Hello, everyone. I hope you all enjoyed the keynote. I know I did. And I hope you all are enjoying your time here at OpenAI's first developer conference. So in this breakout session, we're going to be talking about all the different techniques that you can use to maximize LLM performance when solving the problems that you care about most. So just to introduce myself, my name is John Allard. I'm an engineering lead here on the fine-tuning product team at OpenAI. And it's really been a very exciting few months for fine-tuning at OpenAI, right? So back in August, we launched 3.5 Turbo fine-tuning, and we were just blown away by the reception from the developer community. We followed that up with a few important features. So there was fine-tuning on function calling data. There was continuous fine-tuning, where you can take an existing fine-tuned model and continue the fine-tuning process on it. We even launched a full UI for fine-tuning within the platform. Over these last few months, we've been able to work closely with developers from all corners of industry, right? So solo indie developers, developers from startups, and developers from some of the largest enterprise on Earth. And we've been able to see, what are the problems that they're trying to solve? How are they trying to use LLMs to solve these problems? And specifically, how are they trying to use fine-tuning of LLMs to solve these problems? So I hope to share some of these insights with you all today. With that said, I'm going to hand it off to my colleague, Colin, to get us started.
Thanks, John. Hey, folks. Colin. Nice to meet you. I head up our solutions practice in Europe, which basically means working with some of our strategic customers to try and solve their most complex problems. And what you'll probably be unsurprised to hear is that over the last year, optimization has been the most constant focus from everybody, trying to get LLMs reliably into production. And why is that such a focus? Well, optimizing LLMs is hard. Despite all the frameworks, despite all the content that everybody's releasing, all the kind of metrics and all the different tools that people have provided, it's still one of the biggest focuses, and there's still no one-stop shop for how to optimize. It really depends what category of problem you've got and how to approach it. And I think that's what we're hoping to show you today is like framework to figure out kind of what is going wrong and how to approach it, and then the tools that you can use to solve things. So the reason, I guess, starting with the reasons of why it's hard. So it's hard to separate the signal from the noise to know exactly what the problem is. This is the first place. The second thing is that performance can be really abstract and difficult to measure with LLMs. So it can be really difficult to know how much of a problem you have. And even if you know what the problem is and how much of a problem you have, it's also difficult to know which approach you use to solve the problem that you've identified. So that's really the focus for today. So today's talk is all about maximizing performance. So what we're hoping you'll leave here with is a mental model of what the different options are, an appreciation of when to use one above the other, and the confidence to continue in this optimization journey yourselves. So starting off, optimizing LLM performance is not always linear. So a lot of folks present a kind of chart like this, where you start off with prompt engineering, you then move on to retrieval augmented generation, and then you move on to fine-tuning. This is kind of like the way that you approach optimizing LLMs. But this is problematic because retrieval augmented generation and fine-tuning solve different problems. Sometimes you need one, sometimes you need the other, and sometimes you need both, depending on the category of issue you're dealing with. So we think of it more like this. So there's kind of two axes you can optimize on. One of them is context optimization. So what does the model need to know to solve your problem? The other is LLM optimization. How does the model need to act? What's the method that it needs to carry out, or what's the action that it needs to deliver to actually solve your problem? So a typical flow that you see is starting in the bottom left with prompt engineering. With prompt engineering, you can sort of do both. You just can't scale it that well. So prompt engineering is always the best place to start. You can test and learn very quickly. And the first thing you should do, start off with a prompt, get to an evaluation, figure out how you're going to consistently evaluate your outputs. And from there, you can then decide, is this a context problem, or is this a kind of how we need the model to act problem? If you need more context or more relevant context, then you go up to retrieval augmented generation, or RAG. If you need more consistent instruction following, then you go right to fine-tuning. And these two things stack together. They're additive. So sometimes your problem requires both. We're going to give you examples of where folks have just used one or two and where folks have used all of them to solve their problems. So a typical optimization journey often looks a lot like this. So you start off in the bottom left corner. You've got a prompt, you create an evaluation, and then you figure out what your baseline is. Then, typically, simple next step, add few-shot examples. So give the model a couple of input-output examples of pairs of how you want the model to act. And let's say at this point, actually those few-shot examples increase the performance quite a bit. So let's hook that up to some kind of knowledge base that we can industrialize that process. And that's usually where folks will add some kind of retrieval augmented generation. let's say that now, okay, it's now got context, but it's not producing the output in exactly the format or style that we want every time. So we might then fine-tune a model. Then a classic next step is then maybe the retrieval is not quite as good as you want it to be. Maybe that content could be more relevant to what the model needs. So you then go back and optimize the retrieval augmented generation again. And now that you've optimized the retrieval augmented generation again, you want to fine-tune your model again with these new examples that you've introduced with your updated retrieval augmented generation. So bit of an example here of like the classic optimization flow that we see. And if I could summarize it in like the simplest possible terms, you try something, you evaluate, then you try something else. So that's like in the simplest possible terms. So let's dive into each of these quadrants now. So we're going to start in the bottom left with prompt engineering. Then we're going to move on to retrieval augmented generation, fine-tuning, and then we're going to take all this for a spin with a practical challenge that myself and John took on and show you how this works in practice. So, prompt engineering. Now, I know most of you in the audience are going to be very, very familiar with this, so we're going to kind of skip through this at a fair rate, but always best to start and just make sure everybody knows the principles here. So, prompt engineering. A few strategies here. This comes from the best practices on our documentation, but just to recap them. So first of all, writing clear instructions. I'll show an example of what that means, but this is often where folks fall down in the first place. Secondly, splitting complex tasks into simpler subtasks. If you can imagine that the model is like trying to make a prediction or a series of predictions for every kind of subunit or subtask that you're giving it to solve, you should give it as specific instructions as possible to break down that problem so that it has a better chance of carrying it out. Similarly, giving GPTs time to think. I'll give you an example of a very common framework that people use to do that. And the last thing, I've kind of alluded to this already, but testing changes systematically. So many times we see our customers end up in this sort of like whack-a-mole situation where they change one thing, they change another thing, they change another thing, and they're just they're jumping all around on their evaluation matrix, and they don't feel like they're going in the right direction. And this is really where you need a solid set of evals and typically some kind of like LLM ops so that you can just systematically measure these things as you change them. After that, the most common next step is then to extend it to like reference text or giving it access to external tools, which takes us more into the field of like retrieval augmented generation. But first of all, let's recap what these look like in practice. So first of all, a couple of intuitions for prompt engineering. So prompt engineering, I've said it a couple times, I'll say it again, best place to start and can actually be a pretty good place to finish depending on your use case. So what it's good for? Testing and learning early, and when pairing it with evaluation, providing a baseline to set up further optimization. Should always be where you start. What it's not good for? A few things. So introducing new information. You can pack quite a bit of information into the prompt, and actually with GPT-4 Turbo, you can now pack a ton of information into the prompt. But that said, it's not a super like scalable way to do that using prompt engineering, and we'll see a couple of ways that we can approach that using other methods. Also, reliably replicating a complex style or method. Again, limited by the context window in terms of the number of examples that you can actually show to the model. So it's a great place to start, but depending on the complexity of your task, might not get you there. And the last thing is minimizing token usage. A very common problem with prompt engineering, you keep hitting problems and keep adding more and more facets to your prompt to actually deal with those problems, and you end up using more and more and more tokens, which then costs you latency, cost, all these sorts of things. So again, not a prompt engineering, not a great way of dealing with that particular problem. So, quick recap of like things not to do, things to do with prompts. So we've got a pretty bad prompt here with some vague instructions and some fairly random output. And just recapping a couple ways to improve that. So clear instructions, telling it exactly what it will be presented with and what its task is. Giving time to think. So this isn't a particularly good example here. I'm telling it to approach the task step by step, blah, blah, blah. But really, giving it time to think, I would think of more like things like the React framework, where you get it to like write out its reasoning steps. So it's basically helping itself get to the answer. Like the React framework is just one way that you can approach that, but giving GPTs time to think is another great way of dealing with like where you have some kind of very complex logical reasoning that you need it to do, because it will sort of, I mean, at the end of the day, it's a next token predictor, and it's like, it's printing the tokens that it needs to help it like get closer to that answer, depending on the strength of your prompt. And the last thing is breaking down complex tasks into simpler tasks. So in this case, I mentioned like thinking of each step almost as like a prediction. In this case, just laying them out as clearly as possible. And on the right side, we can see like a fairly nicely formatted JSON output. So again, just the basics, but just wanted to recap those before we move on. So common next step. So prompt engineering, you're trying to like basically tell the model how you want to act, but often it's very difficult to actually know like which of those tokens is actually influencing the model the most. And a great way to start is actually by approaching it as like a show rather than tell problem. So just by providing few shot examples, so giving it input and output pairs and actually showing it the kind of behavior that you want it to have. And this kind of leads us on nicely then to the next step, which is typically folks see some good performance improvement. We're going to see in the practical section that that's what gives us some very good lift with the practical tasks that we take on, but they want to industrialize it, and they want those few shot examples to be contextual, like based on a user's question or based on like whatever the context of this particular problem is. And that's where folks typically take few shot and move on to retrieval augmented generation, or RAG. So for RAG, let's jump right in. So before actually I jump into RAG, I just want to give you like a quick mental model for like how to think of like where to go basically. Because so we started with prompt engineering, we've evaluated, we've identified the gaps, and now we're trying to decide whether it's a retrieval augmented generation that we need or whether it's fine tuning that we need. And it's sometimes useful to think of it as like a short-term memory versus long-term memory problem. So if we think of it as like as perhaps like trying to prepare for an exam. So your prompt is giving them the instructions that they need to complete the exam. The fine-tuning is like all the studying that you do beforehand to learn the like methodology and like the actual framework that you need to answer those questions. And retrieval augmented generation is kind of like giving them an open book when they actually go to the exam. So if they know the methodology and they know what they need to look for, and then retrieval augmented generation means that they can just open up the book, go to the right page, and actually pull the content that they need. And that's why these two things like solve very different things. Without the methodology and without the content, it can be impossible to solve certain problems. And in this case, we're assuming that we've got a short-term memory problem. So we want to give the model the right context that it needs to answer the question. So retrieval augmented generation, or RAG, is all about giving the model access to domain-specific content. So quick recap of like what RAG is. I know, again, most people in the room are going to be familiar, but I'm just going to recap this for the benefit of all. So you'll typically start with like some kind of knowledge base or some kind of like area that you want to get some content to then that you want to use to answer these questions. So in this case, we're going to use like a fairly typical flow, which is we've got some documents, we're going to embed them, we're going to stick them somewhere. Again, I know folks out there probably have their own search services, all their sources of documents that they would use, and that's fair enough. But for this example, we'll assume that we have some documents, we embed them, we make a knowledge base. Then when the user comes in, they're going to ask a question. Let's say, what's the population of Canada? We're going to go, and instead of giving that directly to the LLM, we're going to fire that at our knowledge base using some kind of search. Let's imagine we do like a similarity search. We're going to pull back some content. So we have some content that says what the population of Canada is. And we're then going to combine that with a prompt. So we're going to give it to the LLM and say, here's the question, here's the content, answer this question with this content. And we're going to end up with a, hopefully, correct answer. So quick recap of RAG. So as we did with prompt engineering, I want to share like a little bit of intuition that we've developed in terms of like when you should use RAG and when you shouldn't. So what RAG's good for? Again, introducing new information to the model to update its knowledge. So this is like one of the few ways you can do that now. And it's actually one of the biggest problems that customers come to. They're like, hey, I've got 100,000 documents. I want the model to just know these documents. And unfortunately, right now, there's no like super scalable way to take those 100,000 documents and give the model knowledge of all those at one time. Retrieval augmented generation is probably about as close as you're going to get right now, which is we're going to give some contextual knowledge to it based on the particular problem that you want it to solve. Similarly, reducing hallucinations by controlling content is one of the very common use cases of using retrieval augmented generation. We'll see a bit later how that pairs really nicely with fine-tuning, but a typical use case is you give the model content, you give it instructions to only use that content to answer questions, don't use its knowledge, and then that's like a typical way that folks try and constrain the knowledge to a particular knowledge base and reduce hallucination. What it's not good for, so I alluded to it there, but embedding understanding of a broad domain. Currently, retrieval augmented generation will not allow you to like teach it what a particular like what law or like medicine is. Unfortunately, that's not like one of the things that retrieval augmented generation will let you do. Similarly, teaching the model like to learn a new language, format, or style, like this is probably where you're more in the fine-tuning realm, where you're trying to like teach it a methodology or like a way of approaching solving the problem. And again, reducing token usage. So in fact, you're going to add many, many more tokens in RAG. You're going to keep adding input-output examples. So RAG, I often see folks go prompt engineering and then RAG because the first thing they're trying to do is get the accuracy to a level that they're comfortable with, and then they'll then try and strip tokens back out of this process. And John's going to tell you a lot more about that later. But this is where RAG, you're really like just trying to optimize, give it as much context as it needs to answer the question. And so wanted to share a success story here, because like with prompt engineering and RAG, it sounds like these things like can be quite simple, but they are really quite hard, and it takes a lot of iterations and a lot of testing and learning to actually make this happen for real. And this example, a customer had a RAG pipeline with 2 different knowledge bases and then an LLM, and its job was to get a user's question, decide which knowledge base to use, fire a query, and use that to answer the question. And when we started, we just implemented retrieval, and we had loads of talks with them, and we were all really excited for like how good embeddings was going to be and how easy this was going to be. And our baseline was 45% accuracy. So not so great. What we then tried was a whole bunch of stuff, and I put little like ticks and crosses next to them to show how many things we tried and how many things actually made it into production. So the things with ticks were things that we actually took to production. The things with crosses were things that we tried and discarded. So we managed to boost it to 65% by trying hypothetical document embeddings, where instead of doing a similarity search with the question, you generate a fake answer and do a similarity search with that. And for certain use cases, that works really well. For this one, it did not work well. We also tried fine-tuning the embeddings, so actually like changing the embedding space based on a training set that we had to actually help the model get to the correct answer. And again, this actually worked okay from like an accuracy perspective, but it was so expensive and so slow that actually we had to discard for like non-functional reasons. And the last thing we did was chunking and embedding. So like trying different size chunks of information and embedding different bits of content to try and help the model discern like what were the most relevant. And again, so we got a 20% bump, but we're still fairly far from like something that's possible putting in front of customers. And this was maybe like 20 iterations that we'd gone through to get to 65%. And at this stage, we're kind of like, right, are we going to like pull the plug on this thing? But we stuck with it. And we then tried re-ranking. So applying like a cross-encoder to re-rank the results, or like using rules-based stuff like, oh, well, it's research, so maybe we want the latest document, something like this. And we actually got a really big performance bump from that. And also classification. So basically having the model classify which of these 2 domains it is, and then actually giving it like extra metadata in the prompt, depending on which domain it was classified to help it then decide which content was most likely to be relevant. And in this case, again, pretty good bump. So 85%. We're now looking like we're like just on the cusp of getting to production. And then the last thing we tried was further prompt engineering. So we went back to the start and actually tried to engineer that prompt a lot better. We then looked at the category of questions that we were getting wrong, and then we introduced tools. So for example, we noticed there were structured data questions where it needed to go and pull figures out of these documents. And what we decided to do was instead just give it access to a SQL database where it would just put in the variables and execute a query and then actually bring back structured data answers. And the last thing was query expansion, where somebody asks like 3 questions in one, and you would parse those out into like a list of queries and then execute those all in parallel, bring back the results, and then synthesize them into one result. And these things together got us to the point where we got to 98% accuracy. And at no point in this process did we use fine-tuning. And I want to call that out because, again, as we said at the start, the assumption is often you need fine-tuning to go to production. And actually in this case, it was all like every problem we were dealing with was context. It was all either we're not giving it the right context or it didn't know which of those context blocks was the right one. And that's why it's so critical to know like what is the problem we're solving for here, because if at any point we had gone to fine-tuning, that would have been like wasted money and wasted time. And that's why this is a success story that we're happy with. But I guess I wanted to give a slightly different, oh, cool, thank you. Yeah, sweet. So I wanted to give a cautionary tale as well, because at times RAG, so RAG great, like you have all this great content, the model uses that to answer the question, but it can also backfire massively. And I'll give you a different customer example. So we had a customer where they had one of these, they were trying to reduce hallucination by using retrieval augmented generation. So they told the model you were to use only your content. And then they had human labelers who would check and flag things as hallucination. So one of them, we had a funny guy at the customer, and they said, what's a great tune to get pumped up to? And the model came back with Don't Stop Believin' by Journey. And the labelers were like, right, like this is like definitely a hallucination. But unfortunately, it was not a hallucination. It was actually their content. And somebody had written a document that said, how do I get, like, you know, what's the best way to, the optimal song to energize financial analysis? And it was like, Don't Stop Believin' was the answer. And this is like, this kind of like, well, like sort of funny, is also an example of like RAG. If you tell the model to only use the content and your search is not good, then your model has 0% chance of getting the correct answer. And the reason I call this out is that when you're evaluating RAG, you've actually added a whole other axis of things that can go wrong. It's like we have our LLM, which can make mistakes, and then we have a search, which is not a solved problem. So that's why I wanted to call out a couple of the evaluation frameworks that the open source community have come up with. And I want to call out especially exploding gradients. So they developed this framework called RAGAS, which is cool. And it's, I know, yeah. And it's, it basically breaks down these different evaluation metrics. And you can basically pull it down off GitHub, use it straight out of the box, or just adapt it to your needs. But basically, there's 4 metrics that it measures. 2 of them measure how well the LLM answers the question, and 2 of them measure how relevant the content actually was to the question. So if we start off with the LLM side, the first one is faithfulness. So it takes the answer and it breaks it into facts, and then it reconciles each of those facts to the content. And if it can't reconcile a fact, that's hallucination. And then it returns a number. And if your number is above a certain threshold, you block that because you found hallucinations, basically. This is one very useful metric that comes out of it. The other one is answer relevancy. So a lot of the time, the model will get a bunch of content, and then it will make an answer that makes good use of that content, but actually has nothing to do with what the user originally asked. So that's what this metric actually measures. Is so if you find, okay, well, it's all factually correct, but we have a very low relevancy, that means that the model is actually, we probably need to prompt engineer, or we probably need to do something here to actually make the model pay more attention to the question and actually decide not to use the content if it's not the case. So that's on the LLM side, but the other side is how relevant is the content? And this is where I found it most useful for my customers, because as we alluded to earlier, the classic example with RAG is just putting more and more and more context into the context window. It's hey, if we give it 50 chunks, it'll get the right answer. But the fact is that actually ends up getting the wrong result a lot of the time, where the model there's a paper that was written on this called Lost in the Middle, where it's kind of the more content you give, actually the more the model starts to hallucinate or starts to forget the content in the middle. And actually what you want is the most precise pieces of content. And that's where this metric evaluates the signal to noise ratio of retrieved content. So it takes every content block and compares it to the answer and figures out whether that content was used in that answer. And this is sort of where you start to figure out, okay, well, we're getting really high accuracy, but we've maybe got a 5% context precision. Can we actually bring back much less content and still get correct answers? And this is one of the areas I think where it's really useful for folks to start thinking in terms of sometimes folks get to production or get close to production, and then the instinct is just more and more and more context. And actually this metric gives you a very solid way to calculate is adding more context actually helping us here? And the last one is context recall. So can it retrieve all the relevant information required? So basically, is the relevant information that it needed to answer that question actually in the content? So this is the opposite problem. It's do we have a search, and the stuff that it's pushing to the top and we're actually putting in the context window, is it actually answering the question? So this usually tells you, if this is very low, this tells you that you need to optimize your search. You might need to add re-ranking. You might need to fine-tune your embeddings or try different embeddings to actually bring, surface the more relevant content for it. And I guess I wanted to leave you with that, because that's kind of us trying to squeeze as much performance as we can out of prompt engineering and RAG. But sometimes, again, the problem that you're trying to answer is different. Sometimes it's actually the task that you're trying to get it to perform, which is the problem. And that's where you would take a sideways step and actually try fine-tuning. And that's where I'm going to hand you over to John to take you further.
So let's talk about fine-tuning. So up until this point in the talk, we've been focusing on the prompting family of techniques, right? And so this is where you figure out clever ways of packing the context window of the LLM at sample time in order to optimize the LLM's performance on your task. Fine-tuning is really a different technique altogether from prompting. So just to start off with the definition, right? So fine-tuning, and especially in the context of large language models, is when we take an existing trained model and we continue the training process on a new data set that is smaller and often more domain-specific than the original data set that the model was trained on. And so fine-tuning is really a transformative process where we essentially take a base model, we fine-tune it, and we end up with a different model altogether. And just to step back for a second, the name fine-tuning is really like a great description of this process, right? So we start off with some model that has been trained on an enormous and diverse data set. And these models like 3.5 Turbo or GPT-4 have a lot of very general knowledge about the world. So we take one of these very general models and we specialize them and we essentially hone their abilities to make them better suited for a task that we care about. So why would one fine-tune in the first place? And I really want to highlight like two primary and related benefits of fine-tuning. So first off is that fine-tuning can allow you to often achieve a level of performance that would be impossible without fine-tuning. And just to plant a little bit of intuition here, when you're using prompting techniques, you're limited by the context size of the model when it comes to the amount of data that you can show the model, right? So at the low end, that's maybe like a few thousand tokens. At the high end, maybe it's like 128,000 tokens if you're using Turbo, GPT-4 Turbo. But really, this is nothing compared to the amount of data that you can show a model while you're fine-tuning. It's pretty trivial to fine-tune over millions or hundreds of millions of tokens of data. So you can just show many more examples to a model while fine-tuning than you ever could hope to pack into the context window of even the largest LLM. The second benefit is that fine-tuned models are often more efficient to interact with than their corresponding base models. And there's kind of like two ways that this efficiency shows up. So to start us off, when you're interacting with a fine-tuned model, you often don't have to use as complex of prompting techniques in order to reach a desired level of performance on that model. So you often don't have to provide as complex of instructions. You don't have to provide explicit schemas. You don't have to provide in-context examples. What this means is that you're sending fewer prompt tokens per request, which means that each request is both cheaper and generally responds quicker, right? So it's more latency and cost efficient to interact with fine-tuned models. Next is that a common use case for fine-tuning is essentially the distillation of knowledge from a very large model like GPT-4 to a smaller model like 3.5 Turbo. And so it's always going to be just more efficient from a cost and latency perspective to interact with a smaller model than a larger model. So let's look at an example here, right? So this is an example of like a common task that someone might want to solve with LLMs. And so what we're doing here is we're essentially taking a natural language description of a real estate listing, and we're trying to extract some structured information about that listing. Okay? And so if we were going to try to solve this without fine-tuning, we would essentially open up the toolbox of prompting techniques, and we would write some complex instructions. We would provide maybe an explicit schema that we want the model to output. Here it's defined as like a pydantic model in Python. We would maybe even provide some in-context examples to the model. And so we would then give the model a real estate listing in natural language, and it would provide us some output. And the output's pretty good, but here there's actually a mistake. And it's a pretty trivial mistake, right? Instead of extracting the date that we desired, it templated it to be the current date. So this would be pretty trivial to fix, right? We could add a new rule, we could essentially add a new in-context example, and we could probably fix this problem. But let's see how we would approach this with fine-tuning. So with fine-tuning, what we're going to do is we're going to start with a relatively simple data set, right? So here we have examples, and I want you to notice the simplicity of these examples. There's no complex instructions. There's no formal schema. There's no kind of like in-context examples. All we're giving are natural language descriptions of the real estate listing and then the desired structured output. So we take this data set and we fine-tune a model. Then we take this fine-tuned model, we give it a new real estate listing, and we can see that it essentially gets the problem right in this case, right? So this is just a simple example. But in this case, the model is both performant and efficient. So at sampling time, we don't have to provide the complex instructions, no in-context learning, no explicit schema, and the model does better than we were doing with just prompting techniques. So fine-tuning can be a rather involved process, and so it's important to set appropriate expectations about when fine-tuning is likely to work for your use case and when it's not likely to work. So fine-tuning is really good for emphasizing knowledge that already exists in the base model. And so an example of this might be like a text-to-SQL task. So you have these very powerful general base models like 3.5 Turbo and GPT-4, and they really understand everything there is to understand about SQL, right? The SQL syntax, the different dialects of SQL, how databases work, all of these things. But you might want to fine-tune the model to essentially emphasize a certain like SQL dialect, or to coerce the model to not work its way into edge cases that are specifically error-prone, right? So you're essentially taking the knowledge that exists in the base model and you're emphasizing a subset of it. Fine-tuning is also really great for modifying or customizing the structure or tone of a model's outputs. And so one of the early killer use cases for fine-tuning was to coerce a model to output valid JSON, right? Because if you're trying to interact programmatically with a model, getting out something that is valid JSON is very easy to deal with programmatically. If it's invalid JSON, that kind of opens up many error cases. And finally, teaching a model complex instructions, well, this is for the reasons I mentioned earlier, right? It's just you can show a model during the fine-tuning process many more examples than you could ever hope to pack into the context window of a model. So on the other side, fine-tuning is really not going to be good for adding new knowledge to the model, right? The knowledge that existed in an LLM was impressed into that LLM during these very large pre-training runs, and you're essentially just not going to be able to get new knowledge into it during these limited fine-tuning runs. So if you're trying to get new knowledge into the model, you really want to look at something like RAG for all the reasons that Colin just mentioned. Next, fine-tuning is not great for quickly iterating on a new use case, okay? If you're fine-tuning, it's a relatively slow feedback loop. There's a lot of investment, right, for like creating the data set and all these other components of fine-tuning, so don't start off with it. So I want to essentially look at a success story of fine-tuning, and this one comes from our friends at Canva. So the task here was essentially to take a natural language description of a design mock that the user wanted, to give it to an LLM and have the LLM output like a structured set of design guidelines. They could then use those structured design guidelines to generate a full-size mock and present that to the user, right? So it's essentially a quick way to just throw out some ideas and get a full-size mock. So here the user says something like, I want like a red gradient, I want a profile photo, maybe in the style of an Instagram post. It goes to the LLM, and it's supposed to output something that's very structured here. So it has a title, it has a style with a few keywords from a known set of keywords, it has a description of the hero image, and then it has an actual search that they would give to an image search engine to generate images for these full-size mocks. So what Canva did is they essentially started off with 3.5 Turbo in the base model, and then they started off with GPT-4. And they wanted to essentially see what was the performance on this task, and the performance wasn't great. And so they were essentially evaluated by expert human evaluators. And what they found were that while these models could output sensible outputs, the outputs were actually irrelevant when looked at from like a design point of view. So they then went on to fine-tuning. And so they essentially fine-tuned 3.5 Turbo for this task, and we're really blown away by the results, right? So it not only beat the base 3.5 Turbo model, but it actually drastically outperformed GPT-4. And so what we're seeing here on the scale is that while 3.5 Turbo and GPT-4 often output sensible but irrelevant design mocks, fine-tuned 3.5 Turbo was often outputting rather good design mocks when evaluated by expert evaluators within Canva, right? So if you want to think about like why this use case worked, to start off, no new knowledge was needed, right? All the knowledge needed to solve this problem existed in the base model, but the model needed to output a very specific, it needed a very specific structure of the outputs. And then they used very high quality training data, and they had really good baselines to compare it to, right? So they essentially evaluated 3.5 Turbo, they evaluated GPT-4, they understood where they were succeeding and where they weren't, and so they knew that fine-tuning was going to be a good technique to approach for this task, or to use for this task. So I now want to talk about a cautionary tale for fine-tuning. And so there's this author of this great blog post that I really liked, and they had been experimenting with AI assistants to be writing assistants, right? And so they tried ChatGPT, they tried a few base models from the API. They were impressed, but they were disappointed that these models weren't capturing their tone, right? They have a very specific tone that they use when they're writing blog posts or social media posts or drafting emails, and the base models just weren't capturing this tone. So they had a great idea, and they said, I'm going to download 2 years worth of Slack messages, 140,000 messages in total. They wrote a script to format these Slack messages into a data format that's compatible with fine-tuning, and then they fine-tuned 3.5 Turbo on these Slack messages. Right, so a long process, you got to collect the data, aggregate the data, massage it into a format that's compatible with fine-tuning, fine-tune the model. They finally go through this process, they get a fine-tuned model, and they ask it to do something, right? So they say, can you write me a 500-word blog post on prompt engineering? And this model, this personalized writing assistant responds, sure, I'll do it in the morning. So I'm sure a little surprised and shocked. He follows up and he's like, I prefer if you wrote it now, please. And the model says okay and then does nothing else, right? And so, I mean, we really got a kick out of this on the fine-tuning team, and the author was a really great sport. But if we take a step back for a second, fine-tuning really worked here, right? So essentially, what the author wanted was a model that could replicate their writing style. And so what they got was a model that could replicate their writing style, but their Slack writing style. And if you think about how you communicate on Slack, it's very terse. It's in a stream of consciousness style. You're often foregoing punctuation. You're foregoing kind of grammatical correctness. And what they got was a model that replicated that, right? So while fine-tuning a model to replicate your tone is actually a relatively good use case for fine-tuning, the error here was they didn't like fully think through whether the data that they were providing the model really replicated the end behavior that they wanted from that model. So what they probably should have done here was, take 100 Slack messages, 200 Slack messages, fine-tune the model, experiment with it, and see, is it moving in the right direction, right? Is it getting closer to the tone that I want the model to replicate? They would have seen pretty quick that that was not the case, and maybe they would have gone and fine-tuned it on their emails or their blog post or their social media posts, and maybe that would have been a better fit. We've seen some examples, we've developed some intuition, so how does one actually go about fine-tuning a model? So like any ML problem, the first step is you got to get your data set, and like with most ML problems, this is actually the most difficult part. Some ways of getting a data set, right, you can download an open source data set, you can buy data on the private markets, you can pay human labelers to essentially collect the data and label it for you, or you can often distill it from a larger model if the terms of service of that model support that specific use case. But some way, you essentially have to come up with a data set to fine-tune on. Next, you're going to go and actually kick off the training process. And so this varies a lot depending on how you're trying to do the training. If you use a turnkey solution like the OpenAI fine-tuning API, this can be relatively simple. If you're trying to fine-tune an open source model, totally doable. You're just going to have to get your own GPUs, use a framework. It's a little bit more involved. But it's important while you're training to essentially understand the hyperparameters that are available for you to tune during the training process, right? Are you more likely to overfit? Are you more likely to underfit? Are you going to fine-tune it to the point of kind of catastrophic forgetting? It's important to just understand the available hyperparameters and the impact that they have on the resulting fine-tuned model. Next, I want to point out that it's really important to kind of understand the loss function, right? So when you're fine-tuning an LLM, really, when you're looking at the loss function, it's a proxy for next token prediction. This is great when you're fine-tuning an LLM, but next token prediction is not often super well correlated with performance on the downstream task that you care about. So if you think about code generation, there's many different types of ways to write code to solve a single problem. And so if you're just doing next token prediction and exact token match, the loss or change in the loss function for a model might not correlate to the change in performance on the downstream task, right? So it's important to understand that. Next, you want to evaluate the model, right? And so there's a few different ways of evaluating the model. You can essentially get expert humans to look at the outputs and actually rank them on some scale. Another technique is that you can essentially take different models, generate outputs from them, and then just rank them against one another, right? So not having an absolute ranking, but doing something like an ELO score that you get from chess. You can also do something like have a more powerful model rank the outputs for you. This is really common using GPT-4 to rank the outputs of fine-tuned open source models or GPT 3.5 Turbo. And finally, you want to actually deploy it and then sample from it at inference time. And so these last 3 points can form something of a feedback loop and a data feedback loop, right? So you can essentially train the model, evaluate it, deploy it to production, collect samples from it in production, use that to build a new data set, downsample the data set, curate it a bit, and then fine-tune further on that data set, and you get something of a flywheel going here. So we've talked about a few of these up until this point, but I want to formalize some of the best practices that we recommend when it comes to fine-tuning, right? So first off is just start with prompt engineering and few-shot learning, right? These are very simple, low investment techniques. They're going to give you some intuition for how LLMs operate and how they work on your problem, and it's just a great place to start. Next is that it's really important to establish a baseline before you move on to fine-tuning, right? So this kind of ties back to the success story for Canva. They experimented with 3.5 Turbo, they experimented with GPT-4, they got a really good understanding for the ins and outs of their problem that they were trying to solve. They understood the failure cases of those models, they understood where the models were doing well, so they understood exactly what they wanted to target with fine-tuning. And finally, when it comes to fine-tuning, start small. Don't download 140,000 Slack messages and then just kind of do it in a single shot. Develop a small, high-quality data set, perform the fine-tuning, and then evaluate your model and see if you're moving in the right direction. So you can do something like an active learning approach here, right? Where you fine-tune the model, you look at its outputs, you see in what areas it's struggling, and then you specifically target those areas with new data, right? So it's very intentionally investing. And it's really important that when it comes to LLMs and fine-tuning, data quality trumps data quantity. So the data quantity part of the training process was done in pre-training, right? Now it's you really want to focus on fewer high-quality examples. And just to talk about fine-tuning and RAG, right? So if you want to kind of combine these together for certain use cases, it can be the best of both worlds. So often how this works is that you fine-tune a model to understand complex instructions, and then you no longer have to provide these complex instructions, few-shot examples at sample time, right? So you essentially fine-tune a model, it's very efficient to use. What this means is that you've essentially minimized the prompt tokens that need to be provided at sample time, okay? Because you no longer need to do complex prompt engineering, it's baked into the fine-tuned model. And this means that you have more space for retrieved context. And so you can then use RAG to inject relevant knowledge into the context, and the context that's available has essentially been maximized in this point. Now, of course, you have to be careful to not oversaturate the context, as some of it might have spurious correlations with the actual problem that you're trying to solve, but it essentially opens up room in the context window to be used for more important purposes. So with that said, we've been talking about theory up until this point in the talk. We're now going to talk about application of this theory. So I'll turn it back over to Colin to get us going.
Thanks, John. Cool. Yeah, so let's take all this theory for a spin. So the problem we decided to take on was the Spider 1.0 benchmark. So effectively, given natural language question and a database schema, can you produce a syntactically correct SQL query that answers that question? So an example looks something like this. So given this database schema and given this question at the bottom, can we produce that SQL query on the right? So classic problem, lots of different attempts on it. And what we did was follow the kind of advice that we've given you folks. So we started off with prompt engineering and RAG. And if I just share like some of the different methods we use, just to like get into the details of what we tried, we started off with like the simplest possible RAG approach. So we started a simple retrieval, so like just cosine similarity, use the question and find SQL queries which answered similar questions, basically. So do a similarity search with the question. We also tried formatting the embedding differently. We tried a bunch of prompt engineering just with a couple of isolated examples. And our results were, as you'll see in a second, not super good. So what we did was we kind of thought about this problem, and we're like, actually a question could have a totally different answer if it has a different database schema. So really doing a similarity search with a question doesn't make a lot of sense for this problem, but using a hypothetical answer to that question to search might give us actually much better results for this problem. So what we did was use hypothetical document embedding. So we generated a hypothetical SQL query, and then we used that to similarity search. And we actually got a really large performance bump with that for this particular problem. We also tried contextual retrieval, where just simple filtering, we figured we kind of like ranked the hardness of the question that we got, and then only brought equal hardness examples back in our RAG, basically, if you see what I mean. And that got us like slightly better improvements. We then tried a couple of more advanced techniques. So there's a couple of different things here. You could try like chain of thought reasoning. So you maybe try and get it to identify the columns and then identify the tables and then build the query at the end. But what we settled on was actually sort of fairly simple. We went with a self-consistency check. So we got it to actually build a query, run the query, and then we gave it the error message if it messed up, and gave it a little bit of annotation, and then got it to try again. And it actually got, like, again, sort of funny, but like getting GPT to fix itself. But it's something that we see actually work fairly well if you have a use case where like latency is not a huge problem that you're worrying with, or cost. And the results we got looked kind of something like this. So I'm going to come over here to talk through this. So on the far right was where we got to with prompt engineering. So not so great. So we started off with 69%. Then we added a few shot examples and got a couple of points of improvement. So that told us that RAG could actually give us further improvement here. So we tried with the question, and you can see that we got a 3% performance bump. Then using the answer, so the hypothetical document embeddings, we got a further 5%. Which is pretty cool. So actually, just by using a hypothetical question to search rather than the actual input question, we got a massive performance bump over what we started with. And then all we did was just increase the number of examples, and we got up to 4 points shy of the state of the art with this approach. So again, this is like just a couple of days hacking around, starting off with prompt engineering, moving to RAG, and shows you just like how much performance you can squeeze out of these like very basic starting approaches. And at that point, we decided to turn over to fine-tuning and see whether we could take it any further. And that's where I'll hand on to John. There.
Yeah, so for fine-tuning, we turned it over to our preferred partners for fine-tuning at Scale AI. And so they started off by establishing a baseline, as we recommend, right? So the same baseline that we saw on the previous slide of 69%. This is just with simple prompt engineering techniques. They then fine-tuned GPT-4 with simple prompt engineering techniques where you just kind of like reduce the schema as it goes into the example, right? So very simple fine-tuned model, a little bit of prompt engineering, and they got all the way up to close to 82%, right? So we're now kind of within striking distance of state of the art. They then used RAG with that model to essentially dynamically inject a few examples into the context window based on actually just the question, so not even very advanced RAG techniques. And they got 83.5%, which got us really right within striking distance of state state of the art. And I think the thing I want to highlight here is that if you look at the Spider leaderboard on the dev set, the techniques used are very complex, right? There's a lot of data pre-processing, a lot of data post-processing, often hard coding edge cases into the script being used to actually like evaluate the model. We didn't actually have to use any of that here, right? Just like simple fine-tuning, simple prompt engineering, just kind of following the best practices, and we really got within striking distance of state of the art on this really well-known benchmark. And so it kind of shows the power of fine-tuning and RAG when combined. So just to recap, right, when you're working on a problem and you want to improve your LLM's performance, start off with prompt engineering techniques, right? These are very low investment. They allow you to iterate quickly, and they allow you to kind of like validate LLMs as a viable technique to approach this problem that you're trying to solve. So you iterate on the prompt until you hit something like a performance plateau, and then you need to analyze the type of errors that you're getting. So if you need to introduce new knowledge or more context to the model, go down the RAG road, right? If the model is inconsistently following instructions, or it needs to adhere to like a strict or novel output structure, or you just generally need to interact with the model in a more efficient manner, it's maybe time to try fine-tuning. And it's important to remember that just like this process is not linear. That's really what we want to stress, right? It might take 49 iterations to get to a point that you're really like happy with, and you're going to be jumping back and forth between these techniques, kind of like on your journey. So with that said, we hope you enjoyed this talk. Colin and I will be here for the rest of the day, so if you have any questions.